Hello and welcome back to Calculus 3. All right, the second part of 13.1, double integrals over rectangular regions. We talked about it last time, and we said that the rectangular region is actually a region in the domain which we get because the object that we are observing is having sides that are going straight up. So we have some kind of rectangular domain in our xy plane, and off of those bounds we have the walls that go straight up, and then the top of the object would be whatever kind of wavy surface, which is governed by the function z equals f of xy. So when I drew this last time, I had everything in the first quadrant. Now I'm going to go outside of the first quadrant, so maybe go into all quadrants. So I'll have something that goes like this. As a domain. So we see that on the x-axis it goes from negative number a to positive number b, and then on the y-axis will also go, this is actually not a good drawing. Yeah. These lines were supposed to be parallel, and they are not. So it bothers me. I have to fix this. So it needs to be parallel to y-axis, much better. There we go. And then going this way. Alright, so it goes from negative number a to positive number b on x, and then from negative number c to positive number d on y. And then the object will rise let's say it goes all the way here, and then maybe has this, and then has that, and then whatever. It's some kind of top that is completely. So I'm going to actually shade that top, and that surface there is your z equals f of xy. Now you know that that can contain sines, cosines, e's, ln's, polynomials, whatever, right? But it's important that every face, right, every side is a straight wall, right? And then you have the rectangular domain. So to find the volume of this object, you would take the double integral over region R of that f of xy dA. Now this is the formula which I did not write last time because this is the shorthand formula, and these things mean something. First of all, region R is given as a set of all points x, y such that x is in between A and B, and y is in between C and D. So that's our notation for R. And then we have our dA to be either dx dy or dy dx, depending on the situation. So this is what governs the entire process, right? And then we just solve the integrals in order, the inner one first and the outer one. So let's take a look at problem, I don't know, problem 18. So problem 18 says that we have a double integral on the rectangular region, and then we have x squared plus xy dA, and they give us the rectangular region R as set of all points x, y, they use the, all right, whatever, such that, and then it's 1 less than x less than 2, and then a negative 1 less than y less than 1. Now, you can actually use the rectangular region to draw the domain. It's not necessary, but you can draw the domain, and it's nice to see it. So I'm drawing only the domain. I'm not drawing the 3D, the whole 3D object. I'm just drawing the domain. And I have, as you can see, y's are going from 1 to negative 1, and x's are going from 1 to 2, so this is the region. That's the region, that's R. You see that y is trapped between negative 1 and 1, and x is trapped between 1 and 2. So that's our region. And now if I am to write the integral with limits, first I have to pick whether I'm going to do dx dy or dy dx. And in this case, because you can integrate either way, and you can integrate easily either way, it doesn't matter which one you do first. So let's go with dy dx. That's kind of standard one to have x on the outside, because that will be done last, and you are used to having those calc 1, right? But it doesn't have to be that way. So now, since dx is the outer integral, then the x limits have to be on the outer integral, and the x limits are 1 to 2. And the dy is the inside integral, so negative 1 to 1 on the inside. When we compute this, we copy the outer integral, and then we integrate everything in respect to y, which gives us x squared y plus x over y squared over 2. And we compute that from negative 1 to 1, and we still have dx to deal with for the x integral. So all I did is the inner integral. This is what I solved. And since I was taking the integral in respect to y, all of the x's were constants. So now, they could have called this partial integration, because you remember how to take a partial derivative, right, in respect to x, you hold y a constant, right? Well, you do the same thing now. You are taking the integral in respect to y, so all x's are constants. They could have called it partial integration because you do integrate, but you still integrate everything, right? So, I don't know, whatever. Integral 1 to 2. And now you're plugging in these limits for y's. So that's x squared plus x over 2. And then you plug in negative 1 for all y's. But then it's going to be negative in the formula. So another plus x squared. And then minus x over 2, because the square kills the negative. Yeah, okay, good. And then we still have dx from the dx integral. Dx over 2 cancels. And we have the integral 1 to 2 of 2x squared dx. And that is 2/3 x cubed from 1 to 2, which is 2/3 of 8 minus 1, which is 14/3. So the volume of this object is 14/3. Now, just because it's easy and we can, let's repeat the whole calculation, but now I'm going to swap the order. So I'm going to use negative 1, 1, 1, 2, of x squared plus xy, and now I'm going to do dx dy. So I want to do x integral first. I have to get 14/3 because it doesn't matter if you do xy dx dy or dy dx, unless you have to do one or the other because of the problem, the function inside. But we'll deal with that when we get there. So now let's go. -1 to 1, and we are integrating the inner in respect to x, and I'm getting x cubed over 3 plus x squared over 2y computed from 1 to 2. And I still have dy on the outside because I haven't done the y integral yet. Now I have -1 to 1. Plug in 2, I get 8/3. Plug in 2, I get 2y, so plus 2y. And then I get -1/3. And then I get, when I plug in 1 over here, I get y over, so minus y over 2 dy. For the total of integral -1 to 1 of 7/3 plus, this is 4, so 3/2 y. And now we integrated dy. Well, when I integrate this dy, I'm going to get 7/3 y plus 3/4 y squared. All of that computed from -1 to 1. When I plug in 1, I get 7/3. When I plug in 1, I get plus 3/4. When I plug in -1 and the negative from the formula, I get plus 7/3. And the negative dies, but the other one survives, so 3/4. 3/4 drop, and there's your 14/3. I'm going to write this right in blood over here. For rectangular region, only order dx dy or dy dx does not matter, as long as you bring the limits right properly. So that's what we have. However, f of xy might force you to use one rather than the other. Let's take a look at a problem like that. Something nice. Oof. Beautiful. 22. Look at that. Double integral over the region, and they give you x, y, sine x squared dA. Actually, no, you can do either or here. Let's double this. 44. 44. And region. So, okay, so now you have x to the 5, y squared, e to the x cubed, y cubed. dA. For region R, we have all xy points such that x is between 0 and 2, and y is in between 0 and 1. Great. So now do we do dy dx or dx dy? What do you think? Why? But you also have e to the y there. That's x cubed and y cubed. Yeah, but also if you integrate in terms of y, the x would be constant, right? Why? What? Ah. All right. So, I'm going to write both of these with the reason why pick one rather than the other. Let's do it green. So we have dx dy and dy dx. And now I'm going to just put, equal signs are bad. Put these in, I don't know, whatever. So now if we do dx dy, we actually have to do 2 integration by parts and then u sub to make it. So 2 integration by part plus u sub, because at that point you will strip it off. No, 3 integration by parts, sorry. 3 integration by parts and then u sub. And over here, if you do dy dx, you get to do just a u sub. Huh. Now you're looking at this and say, what? And I say, yeah, Calc2, how are you? So, if you look at the e, has exponents 3 and 3. So, the derivative of y cubed is 3y squared. And I have it right there. So I can use u sub. It's going to go quick. But if I go the other one, the derivative of x cubed is x squared, and I have x to the 5. I have 3 extra x's. And the way you get rid of them is by parts. Because every by parts knocks out one of them. So you have to do 3 by parts to knock this down to 2 so that you can use it with this one to use u sub. So if you have dx dy, probably you can still solve it, but it's like 6 pages, right? Where dy dx is immediately u sub, and it knocks out y instantly, hoping that it will help with x situation. If it doesn't help us with x at all, yeah, we are doomed. We actually have to go through all the extra by parts and things to deal with that. But maybe it will help us. So let's set this up as a double integral x to the 5 y squared ex cubed y cubed. And now we want dy dx. X's are 0 to 2 on the outer, and then 0 to 1 on the inner. Great. So now we have to use our u sub. Let's go blue for this occasion. So u is equal to x cubed y cubed. Now x is a constant. we are dealing with y's. So the derivative of this one, du, would be 3x cubed y squared. All right, sounds good. Dy, obviously, right, dy. So now, to plug in this substitution, the outer limits do not change. Yes. The inner limits will change, but let's hold off on those limits for now. Let's see, what do I need? I have x to the 5, and I need x3. So if I solve over here for y squared dy, I get du over 3x cubed. So when I plug that in, I have x to the 5 y squared e to the u, and now I have du over 3x cubed, and I have a dx there. This is the time to get very excited and very happy, because look what happens. Oh, I was not supposed to put y squared, yeah, because y squared dy, yeah. So now look what happens with this guy. X to the 5 cancels with x cubed, and you actually get x squared, which is what you needed. So we're lucky. So 0 to 2, and then integral, I said hold off with limits. And I have now x squared. Oh no, I don't need the integral now because I want to integrate. I'm going to kick 1/3 in front of the integral, and then have x squared e to the u dx left. And now this e to the u needs to be computed, but I'm not going to put e to the u. I'm going to put back x cubed y cubed, and I'm going to compute that from 0 to 1, because I put limits back. So I have 1/3 integral 0 to 2. I plug in 1 for y, I get x squared e to the x cubed, and then when I plug in 0 for y, I get -1, and I still have dx. So the whole thing over here is 1/3 integral 0 to 2 x squared e to the x cubed, which is great because now I can use one more u sub, and then minus x squared dx. And this is awesome now. I could, but then they're going to have x's in them. So that's why I avoided that. I have 1/3. And now we have another u sub over here. So that's just going to be e to the x cubed over 2, right? Minus x cubed over 3, computed from 0 to 2. That's 1/3. I just stole the same calculation that I had earlier with 3's. Now I have the same calculation with 2's. So has to have the same answer. So what do I have? I need to plug in 2. So this is 1/3 e to the 8 over 3 over 2 minus 8/3, and then minus 1/2. Because when e is equal to 0, x equal to 0, e to the 0 is 1. And then when you plug in 0 there, it's just 0, so nothing happens there. And yeah, this is simplified already. We just have e to the 8 minus 1 divided by 2 minus 8/3. This is exact answer. Now we can obviously get the calculator and get the decimals if you're interested, but who cares? Especially e to the 8. right? Yeah, right? No?
In spinning away into the limit integration of both. So
The zero, yeah. So the reason why I did not change the limits over here, I just left it blank and then I went back to the original limits, is because you have to use your U formula to change limits. So if your U formula is x cubed y cubed, and your limits for y1 is 0 and y2 is 1, then your u1 limit would be, when you plug in 0 here, would be 0, and the u2 limit would be, when you plug in 1 over there, x cubed. So those would be your limits. That's why. And then you would have the integrals look like this, 0 to 2, and then 0 to x cubed. And you would be confusing this with your next section. So that's the reason why I did not change the limits. I just ignored the situation where I'm not supposed to. I'm the guy who always changes limits. But right now, just for the purposes of instruction, I decided not to. I will solve one more problem, and then let's go deal with the review and stuff. Before I go and do any of these problems, we have a few applied problems. So take a look at the picture on the left first, which is it looks like a skateboard ramp, right? And this is exactly something that you would find in one of those skateboard on bicycle courses, so on, right? So you can compute the volume of the whole thing. Here's a wedge of some kind. So you see that they all have a rectangular base, and all of the walls are straight up, right, for the regular buildings. And then you have over here another one with a plane cut. And now you have this paraboloid. But look what they're doing. They are just cutting 1 square inch, right, into it. And this is what I'm telling you as a stencil, right? It's like in a dough. You press a stencil in a dough, and then what do you get, right? How much stuff is inside. And you see that the top conforms to the shape of the object. So whether it's a plane, whether it's the skateboard ramp over there, or whatever it is, right? They all have the same requirement, which is that the top of the function, which is governed by f of xy, has to conform to the shape, right? And all of the walls are straight down, right, cutouts with a stencil. So we can solve any one of these. It doesn't matter which one. 47, 48, 49, 50. Which one?
49.
49. Thank you for picking one. All right, let's go do 49 and then move on with the next stuff. So we have that our z, which is f of xy, is given as 24 minus 3x minus 4y. So that's the plane which cuts the object. Ooh, you know what you can think of? You know, in samurai movies, they miss and they hit the column and they just cut it. Yeah, there you go. So that was a nice square column. It's like with the sword, and that's the cross section. So obviously, as you watch the movie, let's immediately compute the volume, because you know how to do that. You know the double integrals over rectangular regions. I ruin movies for you forever. You'll remember this every time you see it, because it's ridiculous. Also with the watermelon or whatever else.
Maybe it'll excite you when you watch movies, because now you can deal with that.
I know, and you can intimidate those that watch them with you. Right? Let me tell you about the geometry of the bowl for your popcorn. All right. See, this is the elliptical paraboloid. And if you give me the ruler, I'll give you exact equation for it. And then we're going to crank some integrals to find the volume and see how much popcorn we can fit into all of this. You see that?
That sounds like a fun time.
Yeah, nothing gets to the second page. When doing some math.
Yeah, you see that.
Exactly, because that's exactly what it's all about.
I know what I'm doing this weekend then.
If you're lucky to run into someone who appreciates those things, you know, then it's just win every time.
Sure.
All right. So our region of the cut, xy, x is stuck between -1 and 3, and y is in between 0 and 2. Great. So this is one of those problems where it doesn't matter, right? You take a look at this f of x. It doesn't matter whether you do dx dy or dy dx. Let's do dx dy because we can. We did a lot of those dy dx so far. So double integral of 24 minus 3x minus 4y, and let's do dx dy. So outer integral is the y, which means 0 and 2 on the outside, and then -1 and 3 on the inside that correspond to x integral. We are integrating first in respect to x, so it's going to be 24x minus 3/2 x squared minus 4yx. And you know, the most mistakes actually on the exam 3 when you do this and the final is people do one of the two strange things. This is integration, nothing dies, okay? So people either say, oh, I'm integrating with respect to x, and they say that's 0. No, that's for derivatives is 0. For integrals, you pick up x. Or they don't put x there. They actually go at y squared over 2, which is also weird because you're integrating with respect to x. So just make sure when you are in the mode of x integration, all the x's get bumped up, and if there is no x, you just put x because the rest is constant. So 24 gains x, and also 4y is x, constant as well, so it gains x as well. So in terms of the x integral, term 24 and 4y are the same. They're both constant terms. So they each get an x. Right? Because when you integrate 3, you get 3x. When you integrate pi, you get pi x. When you integrate y, you get yx. So that's that. And then you're obviously integrating x over here, so that's x squared over 2. So that's the known term. Now you compute this. All of your x's are picking up 3's and 1's, the -1. So 0 to 2. 24 times 3 will be 72. Minus x squared, that's 927 over 2. Minus, and this is 12y. Now minus, and we plug in a -1, so plus 24, because minus and minus, right? Now x squared, that kills the minus, but you have a minus, and the minus, this is 3 plus 3/2. And then over here you have a minus from the formula, minus from the term, minus from the -1. So that's 3 minus signs all together. And we get 4y. We still have dy at the end because we did not do the y integral yet. So now this is 0 to 2. 72 plus 24, that's 96. Minus 27 plus 3 is -24 divided by 2 is minus 12. Minus 12 minus 4 is minus 16y. dy. So we have integral 0 to 2 96 minus 4 is 84 minus 16y dy. And this is the calc one now. So it's 84y minus 16 over 2, which is 8y squared, computed from 0 to 2. These are all polynomials, so we don't have to worry about 0. 2 times 84 is 168, minus 8 times 4 is 32. And again, don't worry about the 0. You worry about 0 only when you have cosine or e, right? So this is 134. No, 136, sorry. Now, I am going to end here with 13.1, but I am going to ask you to write in your notes to do this integral dy dx. Right? That should be your first homework exercise. So you go home, you read the section, and then the first exercise should be to do the same integral I did here, but do it in the opposite order to get 136. You do have an example of that where I did black and blue. I have problem 18. I did dy dx, and then in blue I did dx dy, and the answer was 14/3 either way. Then we've seen a problem where, I mean, if you like pain, sure, you know, do it with 3 integration by parts and then u sub, or right, do the u sub immediately and then get lucky to do another u sub right after that. So no integration by parts necessary. So some problems will require you to use, I don't know, require, but well, some will require to use one rather than the other, and some problems you can just do whatever is more convenient, or whichever one you want first, it doesn't matter. That's that. What's the next section? Next section is going to introduce double integrals over general regions. So we'll take care of that section after exam on Monday. General regions would be maybe you have 2 intersecting parabolas as your domain, or you might have a parabola that is intersected with a line, and all of those functions are going to go in your limits now of your integration. So we are going to upgrade this this section into a more general case. So that takes care of the integration for now. We are going to switch to the review. I hope you are doing your quizzes and having fun. So let's see. Bye with this.